a voltage source outputting a sine wave, and then we're going to have a resistor, and then we're going to have a capacitor. All right, so we have some resistor with a value R and a capacitor C. Like say, my drawings are really rough here. When I do this at home, I have a sketch pad so I can at least sort of draw on there. But so we looked last time about the impedance in the circuit. And so the impedance is the resistance plus J times X of L, which is the inductive reactance, minus X of C, which is the capacitive reactance. Okay. So in this circuit here, I'm just starting out with a capacitor. So that, of course, means that there is no inductive reactance. And so the impedance of this circuit is going to be just R minus J X of C. So what we got to look at here that we haven't really discussed yet is what is the difference between the capacitance and the capacitive reactance. Okay. So the capacitive reactance is 1 over 2 pi times the frequency times the capacitance. Okay, so this is the capacitive reactance. This is equivalent to resistance in the fact that it impedes current flow. Okay, so the C just means that's the capacitance of the device, right? It's got the 2 plates and the dielectric, and so that's just the capacitance of the device. But X of C stands for the capacitive reactance, and it indicates the opposition to the current flow to an AC voltage. And again, the reason for that is what we are doing here is we are charging and then discharging this capacitor, and that the fact that when we're charging it, we're taking that kinetic energy, that energy due to the electrical charges, the movement of the electrical charges, right, the current flow, we're taking that and storing that into that electric field within the capacitor. And that is, you know, kind of, it doesn't use energy, but it does cause the current, it impedes the current flow. And so that's what this right here is. And the way we calculate that, again, is 1 over 2 pi FC. All right. And that, we could rewrite that in terms of the frequency omega and radians per second, right? Because 2 pi f is omega. And so it'd be just 1 over omega c. So to calculate the capacitive reactance, we have to know the frequency. Okay? We have to know what the frequency is. So let me see here. So let's say that our frequency is the standard 60 hertz. All right. And so if our voltage waveform, if our voltage here is 7.07 volts RMS at an angle of 0 degrees, all right, this is our reference voltage. So normally what we will do is we will shift our voltage waveform. We will look at it when the supply is 0 degrees. Okay, so we'll use that as our reference point. So we can do this. I'll show you in a video I'll do later on this week and post it on oscilloscopes. But we can shift the reference point of waveform so that we can set it to exactly 0. Now in the book, when you look at the problems like at the back of the book, they always give you a non-zero reference point just to kind of throw you off. All right, so I just like to, my supply voltage is my input, and so I can pick when it crosses 0 and call that time t equals 0, and that's my reference. And so I like to just set that equal to 0. And like I say, on an oscilloscope, when we're looking at that in the lab, we can shift that waveform over to a point that we call t equals 0. Okay, because we get to define when that is. But once we define it, we can't shift it anymore. So you need to set it, and then that's going to be our reference. So I typically like to make my voltage my reference point, and so it's got an angle of 0 degrees. However, when we look at this J, okay, this J refers to the square root of -1. All right, so the mathematicians like to use the letter I to indicate the square root of -1. But in electrical circuits, we use I to indicate a current. So to prevent confusion, we use J. We use the letter J to indicate the square root of -1. But what does that mean to us? Well, the square root of -1, I'm not too concerned about that. What this really means for us is it's a 90-degree phase shift. 90-degree phase shift. So what this means is that there is a phase shift of 90 degrees. Now, because this is negative here, because we only are looking at a capacitor right now, it means it's a minus 90-degree phase shift. So when we use J in the circuit, or when we're doing the math and we get a complex piece of the problem here, this means it's a 90-degree phase shift. Okay? 90-degree phase shift there. So what that means is we go back to what I talked about before, right? Eli, the Iceman. Okay, what this means is that the voltage in an inductive circuit leads the current by 90 degrees. Okay, and the current in a capacitor leads the voltage by 90 degrees. So the J, or the square root of -1, is a mathematical term that basically, you know, it gets me, you know, in math, they say this is an imaginary number. Well, in engineering, it's not an imaginary number. I mean, we still call it an imaginary number, but what it really means is there's a phase shift, okay? So there's a 90-degree phase shift. That's what this square root of -1, the mathematical value of square root of -1 in electrical circuits means that there's a 90-degree phase shift. And so if it's an inductive circuit, the voltage is 90 degrees ahead of the current. And in a capacitive circuit, or in a capacitor, so right here in this capacitor piece, the voltage is behind, right? The current is ahead of, in the capacitor, the current is ahead of the voltage, or the voltage is behind the current. Okay? Either way you want to say it. And so, yeah, so it just, like I say, with mathematicians, they say, oh, well, it's imaginary. Well, in physics and electrical circuits, it's not actually imaginary. It indicates that there's a 90-degree phase shift, meaning that the sine wave of your current is 90 degrees behind the sine wave of your voltage, or if it's inductive, you know. So if your voltage is leading here is at 0 degrees is your reference point. So my voltage, okay, that's not a very good sine wave, but my voltage is crossing at 0. That's my reference point at 0. But now my current is going to be 90 degrees off of that. So the current here, if this was at the peak here, the current is peaking here. And so this is a 90 degrees, okay? And this would be for an inductive circuit, all right? But in a capacitive circuit, the current is ahead. So that means the current is already at maximum here. And then it's going down, okay? And so for a capacitive circuit, the current I is ahead of the voltage by 90 degrees in the capacitor. Okay, that's in the capacitor of the circuit. And in the resistor doesn't have the J term with it, so the voltage and the current are in phase in the resistor. So what does that mean for us? Well, it means I need another window here. All right, I'm going to kind of flip back and forth between these here. So now we know that this is the total impedance, right? This is a series circuit. Okay, so this is in a series circuit, and we know that resistors, if we had resistors in DC, right, we had resistor 1 and resistor 2, they would just add together. Well, here, that's basically what I'm doing, is I'm adding these together. So this is in our series circuit here, we have the reactance plus the resistance. The only difference is that the reactance has this minus J coming along with it. Okay, so the reactance has the minus J there. And so what that means is that the current, using Ohm's law, which I discussed the other day, right? Using Ohm's law, the current, trying to clean this up a little bit here. So the current is voltage divided by the impedance. So in an AC circuit, okay, the voltage is equal to, the current is equal to the voltage divided by the impedance. All right, and so if I have a resistor here and I have a capacitor here, then that means that it's going to be the resistance minus J times X of C. All right, so let's say that my capacitance is 221 microfarads. So my capacitance is 221 microfarads. And my resistor is 12 ohms. So my resistance is 12 ohms. And my capacitor is 221 microfarads. Now remember, over here, I gave you the equation for the capacitive reactance. Okay, now notice this is in farads. You can't add farads and ohms, but capacitive reactance is in ohms. Right? I talked about that the other day. Capacitive reactance is given in ohms. And so therefore we got ohms minus ohms. We can do that, right? Or when you're calculating current, right? Current is voltage divided by ohms. And so we need it in ohms, but that's exactly what capacitive reactance is. It's that opposition to current flow, which is measured in units of ohms. And so therefore, we can calculate X of C. Okay, so, but we need to know this frequency. So I said earlier, we need to know the frequency. So a lot of times in your book, they'll like show it to you like this, and they'll say something like, oh, well, the frequency is 60 hertz. Okay, so they'll kind of show us that. And so therefore, now we can calculate the reactance. We can calculate this reactance, which is going to be 1 over 2 times pi times 60 hertz, which is 377. I already calculated that earlier, but I don't know how it came through because of the mic issues, times the 221, okay, times 10 to the minus 6. And if you calculate that, you in fact get 12.002 ohms. Remember, this is reactance, which is measured in ohms. right, so I'm going to write that over here. I'm going to use the e to the minus 6 notation like Octave or your calculator uses. All right, so I did that calculation right over here. You can see that 1 over 2 times pi times 60 times 221 microfarads gives me 12.003. I did it up here. I just used the 377. So remember, that's kind of a round off issue, but we only need to put in the answer to 3 significant digits. So we would put into Blackboard 12.0 ohms. And so I'm not worried about these extra 2 digits here, right? We're only going to submit it to 3 digits. So let me clear some space here. All right, so now our current I then okay, if we calculate the current, now notice this is 12 ohms, and this here now is 12 ohms. But it has the angle in it, so it's minus j times 12 ohms, okay, or 12.0 ohms. All right, and so this is the capacitive reactance of the capacitor. And so when we calculate our current, over here we calculate the current in the circuit, right? We got our voltage, 7.07 at an angle of 0, divided by 12 minus j 12. All right, so when we do that, we can calculate what the current is going to be. Okay. Now the current, if I use the Octave program or you're using the TI-84, I'll resize this a little bit. I'm going to try to increase my font here for you a little bit. Maybe you can see it a little bit better. Font. Okay, did somebody put something in the chat window? No, okay. Yeah, so if you have questions as we go along, please ask. Okay, so what we have here, right, is we have our voltage, E, okay, which is the source voltage. Remember, we use E to indicate that it's a supply voltage, where we just use like V's to indicate general voltages. So if I wanted to put this into the calculator, E is 7.07 volts, okay? 7 if you wanted to be just a little bit more accurate, right? Because if it was 10 volt peak, so if it was 10 times the sine of 377 T plus 0 degrees, okay, so that was my E. And so if we convert that to a phasor, okay, that actually would have been a lowercase e. But if we convert it to a phasor, we get 7.071 at an angle of 0 degrees. So you can just put it in right like that inside of Octave or inside of your calculator. All right. And then, so if I wanted to punch this into the calculator, if I'm using the TI-84 or you're using the Octave software here. So if I'm going to punch this in, I can say I is equal to, and I can punch it in like it's shown right over here. And I can just put in like 7.07, and I'll throw in the 1 there, divided by 12 minus J12. But notice the parentheses. Okay, notice the parentheses here, and I can just put that in there. Actually here inside of Octave, I'm sorry, I need to put a multiplication sign. So I need to put minus, I can put 12 minus J times 12, and I get my current. And there is my current, but notice the current is in rectangular form. So this is what we call rectangular form. Okay, and so we have the real part and the imaginary part. So when we're dealing with currents and voltages, okay, when we're dealing with currents and voltages, we want to use polar form. Okay, so polar form has a magnitude and an angle. And so what we have to do is we have to convert this into a magnitude and an angle. So the way we convert that is we do an absolute value of the current. All right, and so we get our current, which is 0.41666 amps. Okay, or 417 milliamps if you want to put it in that. So our current has a magnitude of 416.66 milliamps. But it has an angle, so now we have to calculate the angle. Okay, and I believe we have in Octave, there's an angle. Okay, yeah, so we have an angle of the current. So there is our angle. Now, here's the gotcha. This angle is in radians. Okay, so that number 0.78540 is in radians. Okay, ignore the error. I shouldn't have hit enter there. But this angle is in radians. They tell you that, I think, up here if I read it somewhere. Do they not say it in the help? But that angle is in radians. And so what we have to do is we have to convert it to degrees. So remember, to convert it to degrees, you multiply times 180 degrees divided by pi. And that gives us an angle of 45 degrees. Okay? So when I write down my current, okay, so if I come over here and I wanted to record my current, I would say that the current is equal to 0.416. And remember, we want to kind of keep this out to at least 5 digits for our previous, for our calculations. And I would put at an angle of minus. Now remember, it's minus because this is the minus sign here. So it's, or excuse me, this was a positive angle. This became a positive. See the positive up here? Because you're dividing by the minus j. So when it comes in the numerator, it becomes positive. So this is a positive. So the current is positive 45 degrees. All right, and we know that because of Eli the Iceman. The current is ahead, so this better be a positive. Okay, this better be positive because according to Eli the Iceman in a capacitor, the current is ahead of the voltage, and my voltage was at 0, so I need to be ahead of that. All right, so this is my current. Okay, I have a magnitude and an angle. Any questions about that? All right, so we have our voltage and our current. Now, I could do this when you have the current in Octave. If you're going to use the Octave software, again, by default, it's going to give you the current in a rectangular format. And this is okay, but when you put your current into Blackboard as an answer, it needs to be polar form. All right, this is a valid answer, but it doesn't really tell us what the peak is, or actually this is an RMS. I shouldn't use the word peak, but it doesn't really, looking at this, it looks like, oh, well, the current is almost 0.3. Well, that's not quite true. It's 0.416 because it's just shifted by 45 degrees. So, so like I say, we can get the absolute value using ABS, and then we can get the angle using the angle, but we have to convert it to degrees because we like as people, I think we prefer the degrees instead of looking at it in radians. And so we can do this in one step. So let me show you how to do it in one step. So I'm just going to put like I polar form here, and then I can put a bracket and I can say the absolute value of I, and then comma, and then I can do the angle of I times the 180 degrees divided by pi. And now I get the magnitude and the degrees kind of in one line. All right, so this is kind of a way that you can do it using the Octave software to get it to display that. And what I think is a more, just instead of doing one and the other, you can just do this real quick here. All right. So and one of the nice things about this Octave software is you can hit the up arrow key and recall previous commands. So see, the nice thing about this is if I type all this once, I'll be able to like recall it and get to it very fast. And then I can make changes to it if I need to, which I'm going to here in a little bit. All right. But when you do your calculations, you can't use this to do any calculations. This is just to display it. Okay. And so you have to use this one to do the calculations in the Octave software. So let's now look at our voltage, right? According to Ohm's law, the voltage in a resistor is the current times the resistance. Okay, so let's look at the voltage here. The voltage VR, and the voltage is the current times the resistance. Okay, that's just Ohm's law. That hasn't changed. Okay, and so we can calculate, therefore, what our voltage in the resistor is, or the voltage drop across the resistor is the proper way of saying that. So I'm going to come over here and I'm going to say my voltage VR is equal to my current I, and again, you don't want to use this polar one because that's just a display. You need to use your default I. So I'm going to take I times R. Now R was just 12 ohms. All right, so there is my voltage. But again, this voltage is in a rectangular format. So I want to convert that. So I'm going to use my up arrow key and I'm going to get over here and I'm just going to call this like VR and I'll put maybe an underscore polar. And this is going to be VR and this is going to be VR. And so now I get that the magnitude is 5 volts and the angle is positive 45 degrees. All right, so up here, the voltage is 5 volts with an angle of plus 45 degrees. Okay, that's the voltage across this resistor. Okay, Abdul, you want to use the 4.16? The problem with that is that's the magnitude, but it doesn't give you the angle. You have to also count for the angle. Now, so yeah, you could take the 0.4166, multiply it by the 12, and then tag on the angle. That will work, yes. Okay, so yeah, so you could say, okay, we're going to take 12 ohms times the 0.416, okay, and that'll give you the 5 volts, okay, and then you got to calculate the angle. So then you got to do the angle, and you could say, well, it's 0. Remember, angles 0 plus a 45 degrees. So the angle is because the R resistance has no angle. So that's why I have a 0 there. Okay, plus 45 degrees, and then that then gives you your angle piece of 45 degrees. Okay, so yes, you can just do the polar form. That will work if you're just doing it one step at a time. Okay, so you could come over here and say inside of Octave, you could say your resistance is 12 times a 0.4166. Right, and that'll give you the 5 volts, right? When you take it to 3 digits, that'll give you 5.0 volts. But now you got to add up the angles, okay? Do not forget about the angles. It's very important to track the angles. Okay. Does that make sense? All right, okay, so what I like about the software here, the Octave software, is it remembers all this for you. And so when you do it, you notice that it actually gave me 5 exactly, where when I typed it out this way, just using the magnitude, I ended up having a little bit of round off. Now, when I got back to 3 digits, it was correct. Okay, but here, because when you look at these values here, okay, the I, so if we look at I, and you can view that at any time by just typing I, and you can see the values, but this isn't the exact value. So if you type format long, and then buy again, okay, you see that it actually takes it out to like 20 decimal places, maybe more. Okay, so it actually stores it in a real long format. So I'm going to go back to the short format, but it's actually storing it with all these extra decimal points in here. And so you don't have to worry about round off if you do that. See, if you shorten it and out to 5 digits, I mean, you still end up getting to the right answer. But if you use the values that are already inside the computer, you're going to have very, very accurate values, and you'll never have round-off problems. And you can do this in your calculator also, but you want to store it and keep those numbers, and that just gives it much more accuracy. All right, so now we have the over here we have the voltage across the resistor is 5 volts at an angle of 45 degrees. So let's find out what is the voltage across our capacitor. So the voltage across the capacitor is equal to the current times the minus J. You can't lose the angle. So it's the current times minus J times the reactance. Now remember, the reactance was 12 ohms. So 12, and there is my current. Now, so again, if I come up here and I'm going to change this, like I say, this is just, I really like this software because I can just change the R's to C's and get my values. So now notice that the polar value here, okay, is 5 volts at an angle of minus 45 degrees. Notice that this is minus 45 degrees, but the current is at plus 45 degrees. So what's that say? It says that the current in the capacitor is 90 degrees ahead of the voltage. This is the voltage VC. So the voltage VC is 5 volts at of minus 45 degrees. But the voltage across the resistor is plus 45 degrees. So let's try to draw this. Okay. And I chose the value of my capacitor and my resistance so that it would be a nice right triangle. Usually it doesn't work out that way. All right, so here is my resistance. Let's see, or my VR. So VR is 5 volts at an angle of 45 degrees. Okay. So this has a magnitude of 5 with an angle of 45 degrees. And then VC, now what I'm doing here, let me write out what I'm trying to do first, right? We know from DC that Kirchhoff's voltage law says that the sum of the voltages is equal to 0. All right, so another way of saying that is that the source voltages is equal to the voltage drops. So what I'm going to do, we know E, okay, we know that E is 7.07 at an angle of 0, and that actually should add up then, if Kirchhoff was correct, okay, so if Kirchhoff is correct, then 5 volts at an angle of plus 45 degrees plus 5 volts at an angle of minus 45 degrees should equal the 7.07 at an angle of 0 degrees. And so we can see that here. I can't draw it very well in this paint software, but I'm going to change the color for my capacitor here. Okay. And so this angle here is minus 45 degrees. Okay. And the magnitude of this is 5. And so now if we were to draw this, okay, this is our voltage E, which is 7.07. Really hard to write like this with a mouse. 7.07 volts at an angle of 0 degrees. Okay. So this is called a phasor diagram. Okay. This is a phasor diagram. So we have E, which is 7.07 at an angle of 0 degrees. We have the voltage of our resistor, which is 5 volts at an angle of positive 45 degrees. So it's going up. And so when we add VR plus VC, we end up with E. Okay. And this verifies Kirchhoff's voltage law. So we talked about Kirchhoff's voltage law in DC, and now we're talking about it in AC. No, this, good question there. No, this is all RMS. Let's take a look at it over here in Octave. Okay, so in Octave, remember that you have VC, which is 5 at an angle of minus 45 degrees. And then up here somewhere we had VR, which was 5 at an angle of positive 45 degrees. This is minus 45 degrees. So here, if I take VR plus VC, I end up with exactly 7.071, which is what I started with. And there's no angle there. There's no J term there. It's just 7.07. Okay. 5 at an angle of 45. 5 at an angle of 45 plus 5 at an angle of minus 45 does not add up to 10. It adds up to 0.707. Okay. And these values, all these values here are in RMS. Okay. All these values have been done in RMS. The reason they don't add up to 10 is because even though we have 5 here, 5 is going off, right, up in this direction, right? It's going up in this direction. So we're not going in a straight line. If we were going in a straight line, we would have 5 and another 5, and that would give us 10 out here, wherever 10 would be. But we're not. We're going up in this direction, and then when we get to this point, we're going to add VC, but VC is going down in this direction. And so when you go up and then you go down, you're not going to end up at 10, you're only ending up at 7.07. Okay, and that's why we need trigonometry for this class. Okay. So this is a graphical representation of Kirchhoff's voltage law in an AC circuit. Okay. So Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law, all these still apply just like they did in DC circuits. The difference is we've got to track the phase angle. Okay. You must track the phase angle. Any questions there? All right, so let's take a look at a different problem maybe. Let me see if I can find something here. And okay, the voltage in a capacitor. Okay, Ohm's law says that the current in a resistor is equal to the voltage across the resistor divided by the resistance. Okay. The current in a capacitor is equal to the voltage divided by the capacitor divided by minus J times X of C, where again, X of C is equal to 1 over omega times C. And if we look at an inductor, the current in an inductor is VL divided by plus J X of L, where X of L is equal to omega times L. So this is the capacitive reactance. This is the capacitive reactance. And this is the inductive reactance. So the inductive reactance and the capacitive reactance are opposition, right? They oppose current flow, but they add in a phase shift. They add in phase shift. Okay. All right, so if we let's see, let's look at another example here. You want to do an inductor this time? All right, so all right, let me try and draw this again here. It's just really kind of difficult to draw with a mouse. All right, so here we're going to have a resistor of 100 ohms. And then I'm going to have an inductor. And the inductor, we'll say, is going to be 132.5 millihenries. Okay. So 132.5 millihenries is my inductance. And so the inductive reactance, X of L, okay, is again, it's equal to omega times the inductance L. And so again, if we just stick with our standard 60 hertz frequency, then we calculate okay, so we get that X of L is going to be 2 times pi times 60 times 132 e to the minus 3. Okay. And so that gives 132.6 times e to the minus 3. So that gives us 49.989. So if we take that to 3 digits, it's just going to be 50 ohms. So remember, reactances are in ohms. The units of reactances are in ohms. So we'll just call it 50 ohms here to make it easy. So X of L is, I'm just going to take it to 3 digits here and make it 50 ohms. And I need a voltage here. So let's just say that we have 120 volts. So, 120 volts and an angle of 0 degrees. Okay. And so remember, this is polar form. Okay, so this is in polar form, which means it's an RMS value. All right, so therefore we can calculate our current I. Well, we need to calculate the Z. Okay, so Z is equal to, in a series circuit, which is what we have. Okay, so in a series circuit, Z is equal to R plus J times X of L minus J times X of C. It's just another way of writing it, okay? But I don't have any capacitor here, so I'll just pull that piece out. So Z is our impedance. Remember, Z is called the impedance. The impedance is the resistance plus all your reactants. And our impedance then is 100 ohms plus J 50 ohms. So my current I is the supply voltage E divided by Z, that's Ohm's law. And so we're going to have 120 volts, angle 0, divided by the 100 ohms plus J 50 ohms. Okay. It's just Ohm's law. Nothing special there, really. But we do have to calculate the angles. Okay. And so if we punch this in our calculator here, and again, I really like using this software, but you could punch this into your calculator. If you have a TI-89, I think a couple of you did buy 89s. Okay, when you buy an 89, TI-89 calculator, or if you have one, I mean, you could actually punch this in your calculator like this. You could put like 120, and then there's a symbol, there's an angle symbol in your calculator if you have an 89. Okay, and so you could actually put in 0 degrees there, divided by, and then you could put, you need to put the parentheses 100 comma 50. Their comma in there. I think it's the same key that has the thing. So if you have an 89, you can actually just punch this in on there and do that. On the other hand, if you have an 84, you pretty much have to do it like I'm doing it in Octave. All right. So, so we could calculate our I. One thing I like to use clear. If you do a clear, it'll clear out any variables that you already have, so you don't end up using the wrong symbol. And then CLC will clear the console or the command window. And so I like to kind of do this to clear things out. Okay. So start from scratch now. So I'm going to calculate my I is going to be my 120 volts. Since the angle is 0, I don't have to worry about the angle 0. Okay. So and then we're going to have 100 plus J times 50. And again, that gives it to us in this rectangular form. So I can recall, notice how I got that really, really fast. Okay, so let me show you this. In this Octave, if you're using the Octave software, if I'm going to type, I want the polar thing that I had before, so I'm going to type IP, and now I hit my up arrow key. And so what it does is we're going to find the first one that started with a capital I and then a P. So boom, I got there immediately using one arrow up to get to that. And so this will give me the polar form. So the polar form, my current now is 1.0733 at an angle of minus 26. So I'm just going to paste that over here. Okay. And so it's, let's see, that is in amps. Okay. And so this is my current. This is my total current here for the circuit. Okay. Should have degrees over here. So that is my current. Notice that it's negative because, again, remember Eli, the Iceman. Okay, we have an inductor. The voltage was at 0, so the current is going to have a negative angle because the current is behind. The current is behind in a inductor. It's behind the voltage, so the current is negative now. And so when we do this now, so that's our current. So then we can calculate our voltage across our resistor. Okay, the voltage across the resistor is going to be the current times the resistance. Okay. And the voltage across the inductor is going to be the current times J times X of L. And so now, if we go back here, I can punch that in the calculator here, and I can say VR is equal to I times my resistance, which was 100. And then I could do VR underscore polar, hit the up arrow key, and I'll recall that, and that'll give me that angle. So this is 107 volts. So VR is 107 volts at an angle of minus 26 point, if I'm going to put it in a blackboard, I only need to do 3 decimal places, 26.6 degrees. So that is my V polar, my polar form of my voltage across my resistor. And then VL is my current times J times the 50 ohms. And then I need to recall this. So I'm going to recall the VR. I haven't used a VL yet, so I don't have it in there. So I'll just recall this one. And make sure you change all the R's to L's. Don't miss any. All right. And that'll give me the polar form. So this is 53 volts, 53.7 volts. .7 volts at an angle of plus, that's a plus angle, 63.4 degrees. All right, so then we can calculate our E, okay? E, well, we just, if we do VL plus VR, right, we should get back to E of 120 angle 0. So we get back to that. So let me draw that. So we got VR here is 107 at minus 26 degrees. So that's going to be something like this, where we have an angle of minus 26 degrees. So we have an angle of minus 26 degrees with a magnitude of 107. And then we have VL, which is going up this way. So it's positive 63 degrees with a magnitude of 53.7. And so when we add those together, we should be ending up with 120 volts at an angle of 0 degrees. That's supposed to be a 2 here, okay? All right, so again, this is Kirchhoff's voltage law. We have the voltage across the resistor, which is going down at a minus 26.6 degrees. And then we have the voltage across the inductor is going up with a magnitude of 53.7, but at angle of positive 63 degrees or 63.4 degrees. Okay. And so now I'll try to do a video on this with actually a ruler and a compass and measuring the angles and show you that, you know, if you draw this to scale, it works. So you can actually solve it using rulers and angles and measuring angles and stuff, and you can actually physically draw this out on a piece of paper and verify Kirchhoff's voltage law. Or if you were doing a parallel circuit, the same thing applies, but it would be Kirchhoff's current law. All right, so let's take a look then. Let's look at it from a different perspective. Let's look at it. Let's say that I have a current and I want to find the voltages. Okay, so instead of starting out with the voltages, let's say that we know the current and try to solve it that way. So I don't know, just pick some different values. Let's throw in a capacitor here. So let's like do the full circuit. Let's say we have a capacitor here. Got this line out of the middle of my cap. Okay, so let's say that we have a capacitor. And with this capacitor, I need some values in here. So we have an inductor. And I'm just going to give the reactances. Okay, so we'll have like X of L. And I don't know, we'll make it like 20. Ohms. So it's going to be a positive J, 20 ohms. And let's say that our capacitor is a minus J, 60 ohms. And let's see, so I don't know what my voltage is. But I know that I have a current and I'm just going to pick a value. So I'm going to have a current of 5 amps at an angle of minus 30 degrees. Or let's see, I've got more capacitance, so let me make it a positive 30 degrees. Okay, so let's say that that is my current. Okay, Now I can calculate my voltage. Well, the first thing, we can calculate the impedance. So the impedance Z is R plus J X of L minus J X of C. All right, and so that impedance is going to be 100 plus J20 minus J60, which is going to be 100 minus J40. So you see how the 20 of the inductive reactance cancels out 20 of the capacitive reactance. So we end up with just simply a minus J40. And of course, the units for this is ohms, okay, because it's an impedance. All right. So then we can say that the voltage, the total voltage E, the supply voltage, is equal to I times Z. This is simply Ohm's law. I times Z. And so E is going to be my 5 at an angle of 30 degrees. So 5 at an angle of 30 degrees times 100 minus J40. And so that's going to be my supply voltage. So if I come back to my Octave software, so I'm going to type in CL, hit my up arrow, and clear my screen, and clear everything out so I can start again from scratch. And so I'm going to say that E is equal to, now I have to calculate the I with an angle in it now. So I did this for you the other day, but I'll do it again. We have to, we have 5 times EXP J times 30 degrees times pi divided by 180 degrees, because you have to convert this to radians. So we have pi is on top. We have 30 degrees divided by 180 degrees. The degrees cancel and you're left with radians. Okay. And then we're going to divide by the 100 minus J times phi. So notice the parentheses. You need to be careful. You need to make sure you use all the parentheses in here. And now you can calculate that. And again, in the one thing about the Octave software, it gives it to you in polar form, or rectangular form. And if I want it in polar form, then I'm going to recall this. I'm going to change the I's to E's. Make sure you change them all. And that'll get me the voltage in polar form. I'm sorry. I'm dividing. Okay, so okay, you need to multiply. It's Ohm's law, right? Current, this is the current here. And this is the impedance. You need to multiply. I divided. Okay. All right. So, so this is my E. We need it up here. I used a divide. It needs to be a multiplication. Okay. The spaces around this doesn't matter. I spaced them out to make it a little easier to read, hopefully. But notice your parentheses, they do matter. And then times, because it's Ohm's law, it's I. This was the current I. And this is the impedance. So I times Z. And so now I can recall that polar form again, and I get 538.5 volts at an angle of plus 8.2 degrees, 8.20 degrees. Right? All right, so if I paste this in here, okay, so the polar form of this is volts at an angle of 8 degrees. So if I'm going to put this into Blackboard, okay, so E, I would put this into Blackboard, I would put in 538 period volts. Now, you can argue that you could leave off the period here, but I just kind of recommend to put it in there so you don't forget. At an angle of 8.20 degrees. And so that is how I would put this into Blackboard. Oh, yeah, yeah, you're correct. It is. It's 39. Sorry. Good catch. 539. Yes. Okay. So thank you. 539. Glad to see someone paying attention here, and I didn't just put everybody to sleep. 539. This was volts at an angle of 8.20 degrees. Thank you. So that is the voltage E. That's the supply voltage in this circuit. All right, so now let's find out what the voltage is across the resistor, okay? The voltage across the resistor is pretty easy, okay? We know the current. It's a series circuit. So remember, let me write this down for you here. In a series circuit, the current is always the same, okay? So this current is the same everywhere. And so, but when we calculate the voltage, so if we want to calculate the voltage VR, okay, VR is equal to I, the current, times the resistance. VL is equal to the current times JX of L. And the voltage in a capacitor is I times a minus J X of C. And I've got the minus signs here. It's the minus J or plus J, okay? So, you know, so if we want to calculate these, we can come over here and calculate these. So we do VR is going to be I. Now, I didn't actually store I in here, right? So if we type I, it just thinks it's there. I need to enter I, and I was up here. Remember, we had to convert it into polar form because I had a phase shift. Okay, remember I had a 30-degree phase shift. That was my initial I up here. And so I have to put that in using this notation because I use the, this is just the way it works. And if you're doing a TI 84 calculator and you want to punch it in, you got to do the exact same thing. Okay. The only thing is with your calculator, you would use, there's a button with the E to the X on it, so you would use that, okay, where I just have to type in EXP. All right, so I type that in, so I've got I in here, so now I can type VR is equal to I times, and R was 100 ohms. And then I can do VR underscore P, hit the up arrow key, and convert that into polar form, which is 500 volts exactly, okay, at an angle of plus 30 degrees. So if we are going to type that into Blackboard, VR here is going to equal 500 period. Now you must put the period there for clarity at positive 30 degrees. That's how we would put it in Blackboard. And then we can calculate VL. So VL is going to equal I times J times, remember that X of L was positive 20. Okay, so that is VL, and this is the rectangular form. So now I have to do VL polar to get it in polar form, which is 100 volts at an angle of 120 degrees. So this is going to be 100 period volts at an angle of 120 period degrees. And then VC is equal to I times a minus, use the parentheses, times X of C, which was 60. Okay, and so that gives us that value, but now we need to put it in polar form. I'm just going to recall this and change L's to C's. And that is 300 volts at an angle of minus 60 degrees. So that's going to be equal to 300 period volts at an angle of 60 minus 60 degrees. Okay, so if I was to draw this, I would come over here and I would draw VR is 500. At an angle of 30 degrees. Okay, so I'm going to try and draw this. This is, you really need to try to draw it to scale. And I'm not quite sure. I can't really, in this paint software, I can't really draw it to scale. Let's take 100. I'm going to draw this. I'm going to call that 100. Okay, so this is 100. I'm going to try to do this to scale. I don't know if I can, I'm going to try to do this to scale. So we need 5 of these. Okay, so I need 5 of these at an angle of 30 degrees. So if can I rotate this? Yeah, I can't rotate this to exactly 30 degrees with this software, which is a bummer. So it's just not going to work. But so I'll just try to sketch it by hand. But I'll try to do one on here. So that's not 30 degrees. Okay. So let's say that's about 30 degrees. So this is 500 at an angle of 30. Now VL, let me come down here. I'm going to do VL in green. And that is at 120 degrees. So VL, starting at this point, VL is going this way, 100 at an angle of 120 degrees. So this is 120 degrees measured from here. Okay. Now VC, I'll do VC in red. Okay. And VC is going this way, 100, that's 100, 200, 300. Okay, and again, this isn't to scale, unfortunately, because if it would allow me to rotate it to something other than 90 degrees or 180 degrees, I could do this. But this is at minus 60 degrees. And so now if we pick some other color for E, so this is my voltage E over here. And I draw this line here. This line is going to be 539 with an angle. I can't draw this very straight, but with an angle of 8.2 degrees. And this is verifying Kirchhoff's voltage law, right? So we have E is equal to VR plus VL plus VC. Okay, and this is what that would look like. Come over to Octave, right? And I'm going to look at my voltages. Remember, if you, or maybe I haven't shown you this, if you type who, it will show you, there's your voltage VC, your voltage VL, and I should have a voltage VR here. Okay, so if you type who, you can see that, or if you put an S in there, it shows you like the size of it, which we're not really too concerned about, but it shows them to you in a more of a linear form here. So now if I take, remember the E, okay, E in polar form was 539 at an angle of 8.2, or in rectangular form, it's 533 plus 76.8 J. And so if I take VR plus VL plus VC and I add those together, notice it gives me the exact same value. So you can actually do this algebraically inside of the Octave software. You can add VR plus VL plus VC and it will give you E. Okay, of course, it's given us E in the rectangular form. Okay. Because that's the way it displays it by default. All right. So, but basically what we've done today is we've verified Kirchhoff's voltage law for a series AC circuit. And we've done that. Okay, so we've done that using algebra and using a Phasor diagram, so we could do it graphically. All right, any questions about that? All right, so, you know, quite a bit. I say I'll try to do one up so I can show it to you graphically, or maybe I'll just do this example, but I'll do it graphically when I get working webcam here. I don't know what happened to my webcam when I started out, that it just seemed to be dropping in and out. So I don't know if it was something with the computer I had it plugged into or what. It's actually a brand new webcam. I'm not even sure I've used it very regularly yet. But so anyhow, you know, Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law, those all apply to AC circuits. The difference is that we have to track the phase angles. Okay, you have to track the phase angles. So when you try to add them up, you have to draw, you know, if you wanted to draw it, you can do that, but you have to add them graphically here. Okay, so that you have to account for the angles. Okay, well, that's all I have for right now. I'll let you guys go. Thanks for logging in. Wait, got a question here. If the sine wave starts at 0, does that mean the phase angle is at 0? Yes, that's correct. So if your sine wave is crossing 0 and going positive at time t equals 0, then your phase angle is 0. That is correct, yes.